Here we have another series of IStructE Structural Behaviour Course questions. These are a series of questions because each one is quite short, and for each question we're asked to draw the bending moment diagram. These will be qualitative, even though I guess this is like quantitative because we've been given P and L, but we'll treat this as qualitative anyway. So let's draw the bending moment diagram of this. And what may help in this situation, because we've got a multi-span beam, what may help is actually to draw deflections of these beams. If we, I will use red here. If we have a applied force in one of these end bays, this will cause the beam to deflect downwards. Actually, and let's draw the points where we know it will, that we know for sure. So the supports, the beam has to travel through those points. So the beam will try to curve like this, and the beam without, if we consider the effect of that left hand force alone, if you try to think just to the right of the supports, the left hand force will cause the beam to rise up onto the right. Similarly, we're going to have a deflection on the right, and that will want to cause the beam to go up on the right as well. Now, why is that important? It's because we've also got a force on in the center as well, and obviously that will want to try and cause the beam to go downwards again, like this. But the key question here is the magnitude of the deflection in the center beam less or more than the outer beams? And the answer is less, because of the fact the outer beams are causing the inside span to push up. So why is that important? It's because now when we try to draw the bending moment diagrams, let's use a thicker blue, that will cause this linear load. Bear in mind these are all vertical reactions. Let's use red. These are all vertical reactions. This is a symmetrical structure as well, so these are all equal to each other. So that is going to be a sagging moment at the center. We're expecting a hogging moment at the internal two supports, but the important part is that this is likely to go into sagging again, but the important part here is that this magnitude is lower than the outer spans. So this will be our bending moment diagram, and it'll probably be helpful for you to have drawn the deflected shape to assist you to solve this question. But this is the answer. Here's another beam. We're not given any lengths or magnitudes of the forces, so we're just going to have to work with this. So straight off the bat, we need to draw the reactions. Now, I will draw the first two, but this right hand one, we have to be very, very careful because we have a pin here. If you remember the fact that bending moments are caused only by external forces or reactions, if we cut anywhere along this beam, for there to be any bending moment, there has to be a vertical reaction. But because if we know that this is a 0 moment point, let's say we did have a vertical reaction here, then can you see like that, because there's no external force to resist that reaction, that would cause this leg to spin or rotate around that point there. That would cause some rotation, but the fact is it cannot have a vertical reaction. So we know, maybe I'll just write that don't know if it's easier to write that reaction is equal to 0. No, okay. It'd just be easier just to not have it. And it's a roller reaction. It's a roller support, so there's no horizontal reaction either, which is great. So then we know that this bending moment diagram will be 0 all the way up to the beam there. Then as we've got a concentrated load and we're looking right to left here, we've got concentrated loads which will cause the structure to go downwards, which means that we've got tension on the top side. And because that concentrated load is the only force that we are dealing with, we have a linear variation as we go from right to left. Now is interesting because the moment we go just to the left hand side of this support, we're dealing with 1, 2, 3, like this UDL, 3 forces, which is really, really complicated. So what I'm going to do from here is start from this side of the beam and go left to right. Okay, so we've got UDL load, so we're expecting some kind of parabolic shape, because the longer as we cut from left to right, the longer this length increases, this UDL, the magnitude of the force increases and the lever arm increases. So we have a x squared, or we have a squaring term of the bending moment. So that's a parabola. Plus we've got linear variation due to that reaction as well. So we have quite a classic shape going on here. So this, if we try to draw the deflected shape, that will try to do that. So we know that bending moment has to be parabolic and on the bottom side of the beam, and there's going to be an upwards general trend due to that reaction force. So that is going to go like that, up. There'll be tension there, but also that will be hogging at the central support. And that is our bending moment diagram. That is our answer. Following on from that last question, we've got a slightly more complex beam now, and we have this pin in the center of the beam, and we've also got roller reactions. And now, unlike the last time round, because we have two rollers, we cannot just assume that vertical reaction is going to be 0 on both of them, because they could you can easily get resolve around moments here and have a vertical reaction going up on one and down on the other, or up on that one and going down here. So we cannot assume that these are going to be automatically 0 vertical. But let's try and solve this anyway. Now, what can we do? We have 4 reactions, and let's draw that one in, because I'm fairly certain that's going to be upwards, because we've got concentrated forces pushing down on it either side. I am also fairly confident that that's going to be upwards due to the fact that there's a big concentrating force kind of inside of the beam to it. But it's a bit more kind of hazy once you get like to the right hand side of that concentrated force. What I like to do, if I'm really unsure, is I like to imagine if this were a mechanism, what would happen? What would be happening if this were a mechanism? Or if we just keep pushing it to kind of slightly unrealistic deformations. So let's try and draw in a deformed shape. So I expect the beam to do that. This will be hogging, but due to the fact that we've got some force pushing it down, that I expect some curvature there. And now it gets more interesting here, because I know that beam wants to be pointing down, but it's going to be brought back into, it's going to be pushed upwards a little bit, because if we take the pin there, I expect a kind of shear force going through the pin like that. A pin can't carry moment, but it can carry shear force either through it and either side of it. Okay, so let's draw the two parts of the structure actually. That's going to be really helpful. We're going to have what did I say? I said that that's likely to have a shear force going up there, and then on the right hand side, equal and opposite, we need a shear force going down like that. Okay, so I said up, up, and we've got concentrated forces coming down here. So let's draw what we can so far. We've got bending moments that would come down, and it's hogging at the central the kind of first of the central supports, so that'll go up like that. And the further away we go, as we go along this line here and looking at everything to the left of it, that reaction force will cause more clockwise rotations. Clockwise rotations will want to kind of cause more tension on the bottom side here. So that will go down there. I'm assuming that there'll be a point of contraflexure there. That will go down until we hit this concentrated force, and that's going in the opposite direction. So okay, so that's going to go back up, and we need to arrive at 0 by the time we get to there. So that should be arriving at 0 here. It arrives at 0 because that's a pin. So let's draw this part of the beam in first. And let's delete that red line so we don't confuse the hell out of you. Okay, now fantastic. That's the left-hand side done. I know that's correct. And now let's look at the right-hand side here. We had a shear force at the pin, which is equal and opposite to that shear force there. We can take rotations. Okay, so we still don't know these reactions yet, so we need to find that out. So if let's take well, we need vertical equilibrium at least, so because we've got a shear force going down here, and because this is a free body cut, so this shear force isn't an external load, but because it's free body, we need to consider that. So vertical equilibrium. So actually automatically means that we're going to have some kind of vertical reaction somewhere. Let's take moments around this point here. Because we know we've got a vertical shear force down here, so that will want to rotate the structure in the anti-clockwise direction around that point. So that means, first big clue, we do have a vertical reaction on the inner support, and it goes up. And now, if we resolve moments around this pin here, because we have an upwards force there, this has to be a downwards force here. There'll be different magnitudes because of the different lever arms around the pin, but the fact is there is still some kind of vertical force. Okay, and then let's fill in the rest of the bending moment diagram. As we go along here and look to the right, we're expecting this to, because that's going to try and pull the beam down, that will cause tension on the top side there. And it's a linear variation. Then as we go further along the beam, right to left and only considering the right, we've got this opposite force, so we expect a reduction of the bending moment. And it's a linear variation, and we know it has to reach 0 by the time we get to the pin. And because these are the only two forces, yep, so this is our only gradient change in the bending moment diagram. So we can fill in the rest of it here. And that is our answer.